Imagine for a second that you are standing on this vast stretch of open land. You look down, and the grass is green.
Right, it looks reasonably healthy.
Yeah, it looks fine on the surface, but what you can't see is that just beneath your boots, the soil is, well, it's structurally dead.
Completely dead.
The earth is essentially collapsing from the inside out. It's this invisible global crisis of land degradation, and right now it currently affects a staggering 3.2 billion people worldwide.
Which is, I mean, it's a scale that is almost difficult to wrap your head around. We're talking about nearly half the planet's population dealing with the downstream consequences of soil that, can no longer support natural ecosystems, let alone the actual communities that depend on it.
Welcome to today's deep dive. Our mission today is to pull back the curtain on this exact crisis. We are going to explore the fascinating, complex, and surprisingly high-tech world of land rehabilitation and soil stabilization. Okay, let's unpack this.
We really have a seriously incredible stack of research to guide the conversation today.
We do. We're pulling from a critical review of mine land rehabilitation outcomes, an eye-opening study on innovative tech for restoring degraded lands.
An engineering paper looking at the wild world of geosynthetic materials.
Right. And finally, a deep legal and social analysis of mine closure liabilities.
It's a highly diverse stack of sources, really bringing together engineering, biology, and the law. But they all point to one undeniable reality.
Which is,
Healing the earth is absolutely not just about scattering some grass seed over a dirt patch and hoping for the best.
yeah, we really want to help you understand that fixing this requires a massive paradigm shift. We're talking cutting-edge technology, serious structural engineering, and entirely new legal and cultural frameworks.
Exactly.
So let's start with what we've been getting wrong for decades, specifically the illusion of healing and what our sources call the revegetation myth. We see this really starkly in the South African mining industry.
Yeah, if you look at the history of mining in that region, dating back to the massive diamond and gold rushes of the 1880s, the physical operations themselves usually last about 30 years.
Just 30 years.
Right, but the environmental impacts are generational. For a very long time, the industry operated under a fundamental misconception. They essentially equated rehabilitation with simply leveling out hectares of disturbed land and throwing down a mix of commercial grass seeds.
I was reading that and thinking about it like putting a fresh coat of the absolute cheapest paint you can find on a house that has a completely crumbling foundation.
That is a perfect analogy.
You step back and say, look, it's renovated, but the structure underneath is still actively failing.
The scientific review points out that this approach fails fundamentally because it ignores the soil's organic carbon sources and its moisture cycling.
The actual lifeblood of the dirt.
Exactly. Without those two specific elements, the soil completely lacks the basic chemical and microbial properties needed to actually sustain biological life over time.
So the grass might sprout initially because of the surface treatment, but year after year, the soil becomes what the papers call hard setting. It literally turns into a brick.
Yes, you get severe erosion, massive gullies forming, and alien invasive plants moving in because the native flora just can't survive. You even get situations where the land contributes to poor air quality through spontaneous combustion smog.
Well, wait, wouldn't it just be cheaper for these massive mining corporations to do the rehabilitation right the first time rather than facing massive government fines or ongoing public relations disasters later?
You would certainly think so. But the corporate math they use, specifically something called net present value or NPV, completely distorts reality.
Okay, how so?
Well, in corporate finance, mining companies project their profitability using this NPV model. Environmental rehabilitation is frequently viewed simply as a begrudged, once-off expense that erodes those profit margins.
Meaning the goal is to get it off the balance sheet as cheaply and quickly as possible.
Precisely. Because rehabilitation costs actually escalate much faster than standard inflation, mostly due to rising specialized agricultural and heavy equipment costs. They're almost always severely underestimated in these MPV calculations.
So the financial provisions for cleaning up the mess are treated as a fixed cost allowable, rather than a dynamic living requirement.
Right.
Think about that for a second. You have short-term corporate budgeting where someone in an office needs the numbers to look good for the next quarter, directly conflicting with the incredibly slow, inflexible timelines of biological systems.
Nature doesn't care about a quarterly earnings report.
It really doesn't.
Living systems simply cannot be managed according to fixed timelines and inflexible administrative processes. Soil takes centuries to form naturally, and you cannot rush its recovery to satisfy a fiscal calendar.
Which brings us to the human toll. What actually happens to the people living right next door when a mine closes and this cheap paint job starts to peel?
This raises an important question, especially when we look at the legal and social analysis coming out of Wits University. South Africa actually has highly robust legal frameworks on paper designed to prevent this.
The laws explicitly enforce the polluter pays principle, right?
Yes.
Yes.
The basic idea being if you make the mess, you are the one who pays to clean it up. The frameworks demand that mines submit detailed environmental management programs, comprehensive closure plans.
And they actually have to set aside real financial provisions to get a formal closure certificate?
But there's a massive systemic loophole.
Mm.
The reality on the ground is that large established mining companies often sell off their aging, less profitable mines toward the end of their life cycle to smaller, inexperienced junior miners.
Ah, I see. And these junior companies frequently lack both the financial capacity and the technical experience to conduct large-scale ecosystem rehabilitation.
Precisely. And when those smaller companies inevitably go bankrupt, the sites become what the research calls orphaned.
The reality for the communities left behind is, frankly, terrifying. They are left living adjacent to toxic mine waste, acid mine drainage that actively contaminates their drinking water, and entirely unsecured open pits.
It's devastating.
I want to highlight something from the sources here because it blew my mind. The abandonment of these sites creates a massive security vacuum, leading to the rise of zamazamas.
Yes.
These are illegal mining operations that move into these abandoned, unsecured sites.
When the formal economy packs up and leaves a toxic site behind, a desperate shadow economy immediately fills the vacuum. It is not just an environmental failure, it is the birth of a severe socioeconomic crisis.
Because these operations exist entirely outside of environmental or safety regulations, which just compounds the devastation of the land and puts human lives at extreme risk daily.
And throughout all of this, the local communities are kept completely in the dark. The analysis points out that community consultation is highly sporadic.
To even see a mine's closure plan, community organizations often have to resort to protracted legal applications based on the Promotion of Access to Information Act.
They have to fight bitter legal battles just to find out what the company was legally required to do to keep their own backyard safe.
It points to a fatal disconnect in the system. The laws require financial provisions, but those provisions often don't align with insolvency laws or business rescue legislation when a company goes under.
Plus, if the public doesn't have open access to the data, they cannot hold the corporations accountable. It is a systemic failure of transparency.
It sounds incredibly bleak, but here's where it gets really interesting. Because the second half of our deep dive is entirely about how science and engineering are fighting back.
Yes, we are seeing a global digital and biological revolution in how we reverse land degradation.
The study on innovative technologies provides some phenomenal case studies on this front. We are finally moving away from manual surveys and guesswork.
And moving toward remote sensing and geographic information systems, mapping degradation hotspots directly from space.
I love this part. Instead of a team walking around thousands of acres with a clipboard trying to guess where the soil is failing, we have satellites doing the heavy lifting.
There is a specific case study in Ethiopia where remote sensing was used to identify highly specific erosion-prone areas. Because they could target their reforestation efforts so precisely, they increased the vegetative cover by 38% in just 5 years.
That level of precision is revolutionary for land management, and it translates beautifully to agriculture, too. The study highlights precision agriculture, where they combine automated drip irrigation with digital soil moisture sensors.
In pilot projects across India and Uzbekistan, this technology reduced water usage by 30 to 50%.
While simultaneously increasing crop yields by 15 to 20%, you're using half the water and getting more food, all because you know exactly what the soil needs at a microscopic level in real time.
It fundamentally treats the soil as a dynamic living system rather than just an inert medium, which ties directly into the biological innovations the sources discuss.
Specifically, custom microbes and biochar. I saw biochar highlighted heavily in the notes from the pilot projects in Brazil and Kenya. I know it has something to do with organic waste, but how does it actually heal the soil so quickly?
Well, biochar is essentially a specialized charcoal-like substance produced by baking organic waste in an oxygen-limited environment. When you introduce it to degraded soil, it acts incredibly much like a microscopic sponge.
So it holds on to things.
Exactly. It sequesters carbon, locking it away so it doesn't enter the atmosphere, and it retains water and nutrients incredibly well.
The studies from Brazil and Kenya are mind-blowing on this. By using biochar, they increase soil organic matter by up to 60% in just 3 growing seasons.
Think about that timeline compared to the decades or even centuries it normally takes for soil organic matter to naturally recover.
It's a massive shortcut.
And when you need to deploy these biological tools over vast, totally inaccessible areas, that is where the drone fleets come in.
It's like tactical carpet bombing, but for nature. The paper discusses drone-assisted aerial seeding of native grasses. They are using this heavily in desertified areas of China and Saudi Arabia.
You have fleets of autonomous drones dropping specialized seed balls over massive landscapes, achieving large-scale recovery with minimal human labor on the ground.
It is the ultimate aha moment. We are taking ancient concepts, like making charcoal to enrich the soil, which indigenous cultures have done for millennia, and combining them with artificial intelligence, satellites, and drones.
It is a phenomenal synthesis of ancient wisdom and modern technology. But fixing the chemistry and the biology of the soil is really only half the battle.
Right. Sometimes you have to physically hold the earth together, especially when you are building heavy infrastructure like highways or coastal embankments on top of degraded land.
Which brings us to the engineering paper on geosynthetics. So we've solved the biology, but what happens when you need to physically hold the collapsing earth together to build a major roadway?
Let's talk about traditional soil stabilization first. Historically, if the ground is weak, engineers just mix in cement, lime, or bitumen to harden it up, right?
They do, and the environmental cost of that traditional method is staggering. Cement production alone is responsible for about 8% of global CO2 emissions.
Wow.
And if you're dealing with weak, expansive clay soils, you have to use a massive amount of it. Typically, clay requires the highest cement content, around 12 to 20% by volume, or 3 to 8% if you were using lime.
And even after you pour all that carbon-heavy cement into the ground, chemical stabilization can just crack under the pressure of shrink-swell cycles as the weather changes and the ground expands and contracts.
So geosynthetics, are we just burying plastic in the ground to fix this?
It sounds totally counterintuitive at first glance, doesn't it? But think of it less like burying trash and more like giving the soil a high-tech skeletal system.
Okay, I like that image. It is very much like the steel rebar inside a concrete pillar, but made of specialized, highly durable polymers that reinforce the soil mechanically, not chemically.
And there are several types tailored to specific engineering problems. You have geotextiles, which are permeable fabrics used for separating layers of soil so they don't mix, while still allowing water drainage.
Right. And you have geogrids, which are literally grid structures that interlock with the soil or gravel to provide intense structural reinforcement.
Beyond those, you have geocells, which look like expandable three-dimensional honeycombs that physically confine the soil so it can't wash away.
And geomembranes, which are impermeable sheets used specifically to control fluid seepage and contain toxic materials, like in those mine dumps we discussed earlier.
The 3 rapid-fire case studies in the engineering paper are absolute proof of how well this works. First, a major highway subgrade project in India. They were building on something called black cotton soil, which is notoriously expansive and weak.
Instead of dumping tons of lime, they used biaxial geogrids and geotextiles. Over 5 years, this reduced highway rutting, those deep, dangerous grooves that form an old asphalt from heavy trucks, by 50%.
Then consider an embankment project in Florida, in the USA. They were forced to build over deep, soft clay. Normally, engineers would have to dig all that bad soil out, haul it away, and truck in new material, a massively expensive and carbon-heavy process.
Instead, they layered geocells and geogrids directly over the weak soil. This reduced the settling of the ground by 40% and saved 25% in overall project costs.
And my absolute favorite application, coastal protection in the Netherlands. They're literally battling rising sea levels. Instead of building massive, expensive, carbon-heavy concrete dikes to hold back the ocean, they use geotextile tubes filled with local sand, layered with geomembranes and geocells.
The result, 60% less soil loss. And because it is not a solid, brutalist wall of concrete, it actually allowed natural coastal vegetation to grow right over it, seamlessly integrating the flood defense into the local ecosystem.
What's fascinating here is that geosynthetics do not just solve an engineering problem, they fundamentally solve an environmental one.
By drastically reducing the need for cement and deep soil excavation, they massively cut the carbon footprint of global infrastructure projects while providing superior durability.
So we have satellites mapping the damage, we have biochar acting as a carbon sponge, we have high-tech polymer honeycombs holding the earth together against rising tides. We clearly have the tools.
But as our sources make very clear, Technology and materials alone are simply not enough.
No, they absolutely are not. If the culture of how we manage land does not fundamentally change, the technology will just be another incredibly expensive band-aid applied to a broken system.
This brings us to the proposed ultimate solution from our sources, the land custodianship model.
Currently, mining companies, developers, and governments use standard, low-cost competitive bidding. They hire whoever promises to do the job the absolute cheapest and fastest.
Which usually results in those 2-year contracts that just scatter the cheap seed and walk away. The land custodianship model argues that we need professional land management agencies who operate with a strict 10 to 15-year perspective.
They outline a very specific three-step framework to make this a reality. Step 1 is initiation, covering years 0 to 5. This isn't even about planting yet. It is about foundational soil profiling, calculating organic content targets, and intricate moisture modeling to understand what the land can actually support.
Step 2 is maintenance, spending years 5 to 10. This involves active, ongoing management, weeding out invasive species that try to take over, managing fire risks, and employing defoliation practices to encourage deep root growth in the native plants.
And finally, step 3, relinquishment, which happens at year 10 and beyond. Under this model, the land is only officially handed back to the community or the government when the ecosystem absolutely proves, through hard data, that it can actively cycle nutrients and moisture on its own.
Across various seasons, entirely without human intervention.
If we connect this to the bigger picture, it is about moving society from a purely transactional mindset to a deep stewardship mindset. You are treating the land not as a corporate liability to be quickly discharged, but as a critical societal asset to be methodically restored.
So what does this all mean for you listening right now? Think about how this applies to your own work or your own life. How often do we default to the short-term fix?
The quick paint job on the crumbling foundation just to get through the quarter, the week, or the project deadline. The lesson from the soil is that true stability requires investing in long-term systemic fixes. You have to build the foundation, even if it takes 10 to 15 years to see the ecosystem truly thrive.
To briefly recap our journey through the research today, we've seen that true land rehabilitation demands that we completely move past the illusion of simple revegetation.
We have to demand long-term financial accountability and close the gaping legal loopholes that leave vulnerable communities dealing with orphaned toxic sites.
We have to embrace the incredible technological tools at our disposal, like remote sensing, precision agriculture, and drones, alongside structural innovations like geosynthetics.
But above all, we need a cultural shift toward long-term custodianship. It is a massive, multi-generational challenge, but the solutions are clearly out there.
Now, before we wrap up, we want to leave you with a final, lingering concept from our source material to mull over.
Throughout this deep dive, we've talked about local governments and national laws trying to enforce these 10 to 15-year standards. But what if the real power to change the world's soil lies somewhere else entirely?
The legal analysis cited a fascinating study from Latin America in 2006. They looked at 4 different countries and found a very surprising primary driver of environmental change.
It wasn't local regulators or national environmental agencies.
No, it was international financial institutions.
Consider this. What if the ultimate catalyst for healing our planet's soil isn't environmental law at all, but the strict lending standards of global banks?
These massive institutions are increasingly forcing multinational corporations to adopt international best practices for land rehabilitation just to secure their project funding.
If the corporations don't commit to cleaning up their act to a globally recognized standard, they simply don't get the billions of dollars they need to operate.
It forces us to ask a profound question. Is the path to global ecological restoration actually going to be paved by international finance? When local laws fail due to loopholes or lack of enforcement, can the sheer leverage of global capital force the paradigm shift we so desperately need?
It is a wild thought to leave you with that the banks might end up being the ultimate enforcers of ecology. Thank you so much for joining us on this deep dive. Keep questioning the systems around you, and as always, keep questioning the ground beneath your feet.